Let's talk about quantization errors. It's interesting to know once you input a signal to an ADC at some point, the digital data you'll get at the ADC output will be already determined. In other words, the quantization errors are deterministic, not random. This is why we should call the difference between the input and the ADC output errors a noise. However, as a circuit designer, it is painful if we want to take these errors into account. Fortunately, scientists found that in some circumstances, we can treat these errors like white noise. First, the number of quantization levels has to be large enough to make errors look like noise. For example, if you input a full-screen sine wave to a 3 dB ADC, you'll find the quantization errors show periodicity easily. However, when the ADC is 10-bit, the periodicity of quantization errors become vague and smears out just like noise. This phenomenon also shown in the spectrum. The quantization errors appear as strong harmonics in low-bit case. But as the bit number increases, the harmonics starts to spread out in spectrum just like white noise. This quantization approximation usually fits from 7-bit to 14-bit. The second rule: don't input a signal that is always sampled at the same space points. For example, if we input a sine wave, which had a discrete time period of 16, and the total sampling length is 128, you'll see the input sine wave is sampled at the same point repeatedly every 16 samples. The quantization error shows periodicity in time, which in spectrum becomes harmonics of the input sine wave frequency. So, how can we avoid repeated sampling at the same signal phase point? Let's say the total recording length is m samples, and the input sine wave repeats j cycles in total sampling length m. When choosing the input sine signal frequency, j and m should have no cofactor. Namely, j and m have to be combined. Let's say the total sampling length m is 256. If we input a sine wave that has 3 cycles in its total 256 samples, this means the length of each cycle is 85 and 1/3. So, after the first cycle is sampled out, the next sample of the second cycle, the 86th sample, will be taken from the input at the phase shifted away from 0 degree by 2/3 sample. Similarly, the sample after the second cycle, the 171st sample, will be taken shifted by 1/3 sample from 0 degree. The sample after the third cycle will start at phase 0 just like how the first cycle begins. If we put the samples from this cycle together, we'll see these samples are uniformly distributed without repeating phases. There will be no repeated sampling point in the whole recording length.